Okay. So the one who was recording is fine? Yeah, it's fine. I've managed to enter in now. Are you able to see my sharing? Hello?
Yes.
Okay. So we're going to continue from where we left from. So yeah, so last time we just did the champ, how to calculate the champ, and we said that the champ basically is you have to know the source. Basically, you calculate the force which the source produces, the force which it exerts on another particle. So basically, just a calculation of the source. So you have to see which one is causing the force, which one is exerting the force on another. So if you know which one is exerting the force, that's that's the charge which you are going to use to calculate your champ electric. And we looked at an example. We looked at an example where we see that A, B, and C were the sources which were exerting a force on G, the charge G, and we solved that one. So today, actually, we're going to just finish off. Yeah, we are going to finish with we are going to look at the topography, and also, yeah, the symmetry and the invariance. So topography du champ électrique. When I talk about topography of champ électrique is how is the champ électrique represented in a diagram form? How is it represented in a diagram form? So topography basically is a word which is usually used when you are dealing with the maps, the presentation of geological things on the maps, like the mountains, the rivers, different places. So like how you present it on the map, if those who do geography, they can relate with that. So topography to shampoo electric basically is just a diagram form. How can you present a diagram form, or how does this when this force is exerted on a charge, what usually happens? What usually happens on that force where you exert the where you exert where on that charge where you exert the force? What happens around it? So we're going to see what happens around the charge where you exert the force, and we're going to differentiate if it's positive, what happens, if it's negative, what happens. So those are the things like under topography, those are the things which we're going to look at. So notion de champ. So we see here, it's saying en physique, un champ est un outil mathématique qui permet d'associer à tout point M de l'espace une grandeur physique qui peut varier dans le temps. So here they're just saying in physics, champ, when I talk a champ, it is an util mathematic which permits us to associate at all points of the space une grande physique qui peut varier dans le temps. So here is physical quantities. I think you know about the physical quantities. So when I talk about the champ, I bring in physical quantities, and the champs usually they are related with physical quantities. Physical quantities, I'm talking about the scale. If you know the scalar quantity and the vector quantity, I think you know those things. the scalar quantity, and the vector quantity. According to, I remember in physics, we said that scalar quantity, a scalar quantity is one which only has magnitude but has no direction, and the vector quantity is the one which has magnitude and direction. If I remember correctly in your physics, that's what how we defined the scalar and the vector quantity. So it's the same thing here. So they are saying that. So here they are just saying there's a champ de vector and a champ de scalaire. Un champ de scalaire associé une value unique en tout point M. So they are saying the champ scalaire is associated by a unique value in all points, meaning it only measures the magnitude, it only measures the size, but it doesn't show the direction. For example, temperature. Temperature, you only have, you can either have 0 degrees Celsius, 20 degrees Celsius, 40 degrees Celsius, but it doesn't show the direction where the temperature is going. So, champ scalaire is associé avec une value unique en tout point M, meaning each value is unique. Then, un champ de vecteur associé une direction, un sens et un nom en tout point M. So vector quantity is the one which has the direction, it has the sense, and it has a standard in all points. So you know its direction, you know its sense. For example, I can give an example of a car. A car, it can be moving at maybe 4 kilometers per hour, and in the direction they can specify towards west, towards east, towards south, those things. So that's a vector, champ de vector, a vector quantity. So there's a scalar quantity which only gives the magnitude, and the vector quantity which shows the direction, the sense, and the standard in all points. The unknown, which is standard in 2 point M. So I don't know if it's clear here on scalar and vector quantity. Is there any questions? If you have any questions, you can ask, please.
Oui.
Yes, I'm listening. Hello.
Oui.
Yes, I'm listening. You can ask. I can't get in. Maybe your network is bad because I can't get you speaking. Yeah, is any other with any question? Those who like you are trying to ask questions, if it's not what, yeah. Sometimes my network, you can just write it in the chat so that I check it, then we answer it. Anyone has any question? Another question? So here, basically, I don't need to really break your head or overthink. You just have to know what is a champ the vectors and champ the scalar. And I know these pictures they're not clear, but this picture here, like for this one, is basically just showing the temperature, like in each area, just showing a map and some temperatures in each area. We just showing that the champ the scalar only shows the magnitude. Then this one is just showing the vitesse, which is these lines, they're just showing the movement of, I can say wind. Yeah, I can just say wind. Yeah, but it's not clear. Like for you, it's not really important, the diagram, this diagram. What you should just know is what is the champ scalar and what is the champ de vectors. You have to know that the champ de scalar is the one which only has it magnitude, meaning it only has size. Then the champ de vectors, it has a size and the direction. Yeah, so if there's no one with any question, The one who was asking the question, you can write it. Yeah, I'll check it. So we're still on topography du champ électrique. Now we're going to go on champ, yeah, on champ électrique. We're still on topography. Then, yeah, we're going to champ électrique. They are going to do talk more on champ électrique according to the diagram form, how you can present them in diagram form, all those things. So here, champ électrique, they say, la présence des charges sources dans une région de l'espace modifier les propriétés électriques de celle-ci en créé. En chaque point M, un champ électrique. So la présence des charges sources, so the presence of the source, the presence of the source of a charge in a region of a space, it modifies. So the presence of the presence of the source charge, where the charge is coming from the source, in a region of a space modifies the property electric of what of that one which is what created. So here they're just saying that this source, the charge source, which creates the force, is the one which modifies, is the one which defines how much force will be exerted on another charge. So I can say it's the definer of the property electric, because it's the one which is creating this force, it's the one which is creating a champ, it's the one which is, in other terms, the one which is creating an area which is electric charge, because it's the source. The source is where everything begins. So it's the one which is going to determine the property electric of the champ electric, the area in which there's a electricity, in area which the forces are formed. Is the one which is what is going to is the one which is going to define the properties of electric. And here there's ligne de champ. Le ligne de champ, so les coups orientés tels que l'air tangent sur ligne de champ. Les lignes de champ sont les coups orientés tels que l'air tangente en chaque point et même direction et même sens que les champs électrostatiques. So we have what we call ligne de champ. So you have to know that when you talk about ligne de champ, you have to know that ligne de champ, they are a sort of what? A cube is, they are a sort of, I can say, some caves. They're sort of caves which are oriented in such a way that their tangent, the tangent, if you see this cave, if you see these caves, where here, or like where the tangent, where you can draw a tangent, you see that that tangent, it will be in the same direction as the champ electrostatic. So they're saying that where the tangent is drawn is in the same direction according to the what? To the champ electric. So basically, most of the time, they will give you a cube or a what? A sort of a curve in which they show you the direction. This is the line de champ. This is the line de champ. They show you the direction is going this side and it's coming out the other side. So for you to know your champ in the diagram form, for you to know the direction of your champ, you just draw a tangent where a curve is made. You just draw a tangent where a curve is made. So this one, you have drawn a tangent. So it means since this ligne de champ is moving in a direction which is from, according to here, is moving from left going to right, according to our curve here. The curves, yeah, it's moving from left to right. So when I write my tangent, this tangent will move in the direction towards right, the direction where this linear de champ is moving, and this direction is what is I can say it's the champ electrostatic. You see the champ electrostatic. That's why they're saying their tangent on chaque point et même direction et même sens que le champ électrostatique. So if you know their tangent, but most basically they don't give you like a calculate the champ what, they give you some curves, some what. No, they don't do that. The only thing which they do is they can give you like the one which we did the example. They just give you like a triangle with some charges, or those, then they tell you to calculate the champ electric. So here it's just the phenomenon, some phenomenon which you have to know, some definitions, some things, some facts which you have to know. So what you have to know is that when you have a curve which is called linear du champ, each tangent is in the same direction as the champ electrostatic, which is this one. I don't know if there's any questions here. Is there anyone with any questions? Please, you should be asking questions, because electricity, I can be seeing that I'm explaining, then others they are not. For me, I'll be seeing that I'm explaining the Shinang station. They are not understanding. So it's better you ask, so that when you ask, it even helps me to explain even more. When you ask, I'll even explain more, because there are some points maybe I've forgotten to tell you or what. So where you are not clear, please ask your questions. Yeah, so if there are no questions, we're going to move. So yeah, so what you should know here on topograph to champ, what you should know is the first thing on this chapter, what you should know on this page, what you should know is that the first thing, the source where the source where the charge is coming from is the one which defines is is what it's the one which defines the area or the force which is created around the charge which it exerts. And you should also know, if you have a curve, if you have a cube, which is a French cube, if you have a curve, the tangents which you form on the curve is direct proportion to the champ electric, or is the same, is in the same direction and the same sense as the champ electrostatic. So those are the things which you have to know on topography du champ electric. Then topograph to champ electric, exemple de ligne de champ. So basically we are learning about those linear de champ, so that you just have an idea. If you just have, I can say you just have knowledge or some facts or somewhat under linear de champ. So here there are some examples of linear de champ. So basically you should know that if you have a particle, hello?
I'm saying I have a question.
Yeah, you can ask, please.
Could you kindly repeat what you said? You said the what is directly proportional to what?
Yo, I'm saying, yeah, I was just saying that the direction of a tangent, if you have a cube, then each tangent, I was saying that each tangent is just is in the same direction and the same sense of champ electrostatic, which I was saying that when you have a cube, you draw its tangent, the tangent is direct proportion to the champ in such a way. I was just meaning that it has the same direction and the same direction and the same sense. So for example, you have this cube here, and we drew a tangent here on this cube. You see that this tangent, it is this tangent is representing the champ, because as you say that if you draw any tangent on the linear Deschamps, if you are given a linear Deschamps, then you draw any tangent, that tangent is equal to the Champ electrostatic. It represents the Champ electrostatic, which means that it has the same direction, it has the same sense. So it means that so it means that if you have drawn the tangent, that tangent is equal just to the direction and the sense of the Champ electrostatic. That's what I was meaning. Don't know if it's clear.
Yes, it is.
Yeah. So that's what I was meaning. So some examples of linear Deschamps. So you should know also how this linear Deschamps. So the linear Deschamps is if you have a positive charge particle, if you have a negative charge particle, where does how does it, I can say, the force which is created around that charge, how is it? Is it the force which is going inward? Is it the force which is going outward or what? So you have to know each sign, which is the positive or the negative, has its own linear Duchamp or its own way of showing a champ around it, which shows either whether the force is going outside or inside. So here, for example, if you have a particle which is charged positively, most of the time, its linear Duchamp it shows the arrows which are going outside. Like this, for example, this charged particle, the champ around it, because it's positively charged, it's like it is what it is going outside. That's how a positive charged particle behaves. So that's how a positively charged particle always behaves. But a negatively charged particle, you see that its linear Deschamps is going is like the charge which is created around it, or the not the charge, the force or the electric the electric force which is created around the charge is in a way of like it's coming inside. If you see here the negative one, so these are the topography or the way the charge are presented the linear Deschamps are presented around a charged particle. So these ones actually they're just showing you the diagram, the one they're not really important. The most important thing is you have to know that for a positive, what you just have to know is for a positive, when you create a champ around it, its linear Deschamps is going outward, like it's going outward. And for negative, its linear Deschamps is what coming inward. And when you try to bring the negative, the positive plus the positive, what happens is the same thing which we have been looking. We have looked at over and over. We say that if it's positive, there will be some repulsion. That's why you're seeing here that it is positive. You see there's what repulsion, like they are going, both of them they are separating. They will never meet. They'll always they'll always an repulsion, which shows that they are of the same sign. Then if I bring negative and positive, you see that there will be an attraction. So basically, the way you show the arrows is very important. And these arrows which are here, they're just separating the positive and the negative. The positive, the arrow must be going outside, and the negative, the arrow must be going what? Must be coming inside. And it's logic, because if I bring a negative and a positive, what happens? A positive basically it does, like most of the time, you know that something which is positive, it has lost something, like in your chemistry, in your chemistry. Something which is positive, it means it is losing, and something which is negative, it means it's gaining. So basically, most of the time, you see that the negative part, it has the arrows which are entering, and the positive part, it has the arrows which are going outside. And when you bring them together, you see that the positive will be, it will be like the attraction will be, the arrows of the positive, they will be like they are going inside the charge, the negative charge. That's how it's represented. So this is the topography, which you should just know that if it is the same sign, there will be repulsion. If it is a different sign, there will be attraction. And these, they are presented in the linear de champ. So these are the linear de champ. For positive is outside, for negative is what. But I've never seen a question where they ask you to write the linear de champ, all those things. It's just the information which you should know. Yeah, in case you encounter something which like when you're solving these questions, you have to think in all angles. You have to utilize everything which you use. So in case you find something which is difficult, you can uh, you can be able to easily relate or to easily uh, do something. Yeah, I don't know if there's any question here under the examples of linear Duchamp. Any questions?
No,
Yes, you can ask.
no question.
Oh, no question. Oh, okay. So we're still under topography Duchamp electric. So basically, yeah, so here we're just going to summarize it before we go to another one, and the Champ electric. So the property, the linear Duchamp. So here basically under topography, we're just looking at it. The most important, we're just looking at it, these lines, the linear Duchamp, what happens with the positive and what happens with the negative. So what you should know that the positive is outside, the negative is coming inside. Then now is property, the linear Duchamp is just the summary of it. So the first one is on tout point de l'espace, la direction du champ est tangente à la ligne du champ. This is the thing which we have looked at, the first one, which we say that in all points of the space, the direction of a champ, which is the champ electrostatic, is tangent is a tangent at the linear du champ. So when you have a line de champ, the tangent which you create, that's the direction of what? That's the direction of that's the direction of the champ electrostatic. For example, here, you have seen they are coming together, like you are making a sort of a curve. If I draw a tangent here, the tangent will follow the direction of where these are going. So the tangent will be like going outside here. And you see that this tangent will be equal in all. If you're given two charged particles, basically when you're given two charged particles in this form and they have drawn linear de champ, if they have drawn for you linear de champ, you should know that where you are making a sort of a curve and you draw its what? You draw its tangent. That tangent is equal to the champ electrostatic. So basically, like this diagram, they can just tell you to show the champ electrostatic. So how can you show the champ electrostatic? You see where a curve is made, and you just draw tangents where the curve is made. For example, this one, you see there's a curve, like there's a sort of a curve. You can just draw a tangent according to the direction in which this one is going, then you have your champ electrostatic. Simple as that. If you are given linear de champ, but I've never seen a question where they have given you linear de champ and they ask you to indicate the champ electrostatic. But in that case, in a case where they have told you to indicate the champ electrostatic, you don't have to have any difficulties. You just check where a curve is made, and from there just draw a tangent. So that's what the first point is saying. And the second is saying, une ligne de champ est toujours orientée. Une ligne de champ est toujours orientée. Dans le cas du champ électrique, elle est orientée depuis the charge positive vers the charge negative. So they're saying that when you have ligne de champ, the ligne de champ is always oriented. It's always oriented. So what you should know is that if you have a negative and a positive, a negative is always going outward. A positive is always going outward. Sorry, pardon me. A positive is always going outward, and a negative is always what? Going inward. And you should know that when you have a positive and a negative, for a positive, here they are saying for a positive, it is oriented from inward, going what? outward. Then for a negative, we see, if you have seen for a negative, we see, going what from outward, going what inward into the charge. So this is how it is oriented. So this you have to know under the topograph is important to know. Then le mode du vecteur champ est proportionnel à la densité des lignes de champ. So they're saying that le module, I can say the size of a vector champ, the size of the vector champ, or I can say in other terms, the power of the vector champ is proportional to the density of the linear de champ. So they're saying that if the champ is greater where the lines are more denser. What do I mean? The champ is greater where the lines are more denser. What do I mean? I mean, for example, you have A, B, and C. So here, if I say denser here, density, I'm not meaning the heaviness, but density, I'm meaning the cloudiness. Where is it more compacted? So you see where the line is more compacted, you see, on A here, as compared on B and C. So you see that on A, its module de vector champ is greater than on B. So here, you also have to know that where is more denser, the vector du champ is greater than where it's less denser is the vector du champ. The module the vector du champ is also less. So this one is also a principle which you should know. Then the last point which you should know is that la ligne de champ ne se coupe jamais. These lines de champ, ligne de champ, the line of a champ, they do not cut. They do not cut. They're just saying that they are always in a continuous form. They do not cut. Sinon, which is if not, à l'endroit où elle se couperait, le vecteur champ aurait des directions different. So they're saying that if not, the place where it cuts, the place where you cut this champ, the line, the champ, you have the vector, you have vectors which have two different directions. So if this linear de champ, which is in a form of a curve, it is cut, meaning even the direction will be will be changed. So you should know that the linear de champ is never cut, it's always a continuous, and when you cut it, something has to change. Thus the direction has to change. So the direction of the two has to change. So basically, this is a summary about the topography du champ électrique. I don't know if there is anyone with any question here.
Yes.
Anyone with any question?
Yes.
So yeah, so we have looked at hello? Yes, sir?
Yes, I want you to repeat the meaning of the first statement.
The first statement?
Yes.
Oh,
You have to
okay.
repeat the meaning.
Okay. So the first statement, it says, en tout point de la space, la direction du champ est tangente à la ligne de champ. So they just saying that in all space, the direction of a champ is tangent, or the direction of a champ is tangent at the line of the champ. So they're saying that I gave an example of this one. So what they mean is that in all space where you have two charged particles, if for example it's positive, where you draw a tangent, that tangent is, I can say the tangent of a cube is the same as the champ electrostatic. It's the one which defines the champ electrostatic. What do I mean? For example, if you have positive charge and I try bringing them together, you see that there will be line the line the champ will be like moving outward, and they're making a sort of a curve. So if I'm told to present the champ electrostatic, which is denoted by the sign A. So how do I present it? So when I want to present it, I'll just draw a tangent on this curve. Yeah, I'll just draw a tangent on this curve, and this tangent, it will move in the direction what it like it's moving outward, which means that that tangent is just the same as the what the champ electrostatic. So here, the tangent which I draw, the tangent which I'll draw, since we have already learned that the tangent which you draw on a curve, on a linear de champ, on the line de champ, is in the same direction and the same sense as the champ electrostatic. So meaning that tangent, it is representing what the champ electrostatic. That's what the first statement is saying. Even here, where of course is negative, where you're making like a curve, you draw a tangent, and that tangent is just equal to the champ electrostatic. So you just represent it by E, since we have said that the tangent which is drawn on a curve is just equal to the champ electrostatic. I don't know if it's clear.
Yes, it's clear. Thank you.
Yeah. So I don't know if there's anyone else with any other question. Yeah, so if there's no one, we're going to go to champ créé par une distribution de charge continue. Champ créé par une distribution de charge continue. So so it's just the same thing. It's just the same thing which we the distribution, the formulas for distribution. I don't know if you still remember them. When I say distribution, I told you guys that you should always be thinking of a charge which is found everywhere, which is found anywhere. It's not punctual. Punctual is a fixed charge where you can just find it on the same point. And when you're told to calculate for punctual, it just is for punctual. When you're told to calculate for punctual, you don't need to do differentiation in Q. What you know that your Q or charge Q is on a fixed point. But yeah. So for example, like the question for punctual, which we had is yeah, it's this example. For punctual, we had this example where you have the charges which are fixed in the corners. Yeah, which are fixed, which are just fixed in the corners. They are fixed. That's punctual. Then if I say distribution, meaning the charge, you can find the charge almost anywhere on the area which you are given. So this is all about the distribution of the charge. So if you understand the distribution of the